Hello, everyone. I would like to talk about some activity going on in my research team. We refer to as LEPS, for Laboratory for Embedded and Programmable Systems at ECE Department of UC Davis. My name is Soheil Ghaisi. I'm an associate professor with the ECE department. And the work I will be speaking about today deals with efficient implementation of streaming applications, specifically for convolutional neural networks for mobile vision and mobile applications in general. This work is a continuation of some activity that we have been working on with my grad students and several colleagues on productive programming of many cores. And the activity came about sometime in the 2005-06 the date range. And it was a problem because we have a colleague who manufactures chips with hundreds to thousands of lean cores for energy-sensitive applications. And programming of a platform like that obviously is a challenge. So the question posed to us was, how do you effectively use such a device? And specifically in the context of streaming applications for signal processing, for communication, networking, and applications of that space. And the approach we took was to take a programming by synthesis approach in which we ask the programmer to specify the application with a high-level specification language we refer to as formless that allows capturing of the behavior but allows massaging and malleability of this specification as you go through the software synthesis process. And then we developed a number of task assignment for assignment of application tasks to processors, scheduling for determining the order of execution of these tasks, and eventually this would be handed off to a conventional compiler for binary synthesis. As part of this activity, we came to know vision applications, and this newer ongoing project, which is rather recent in our team, came about on efficient implementation of convolutional neural networks. So let me switch gears and talk about why they matter and kind of talk a little bit about the activity in my team. And this might be known to many people in the vision area, but to sum it up, the idea is that recently, before the past, let's say 4 or 5 years, the predominant way of going about object recognition in the computer vision community was to rely on experts to design hand-engineered features. So examples are SIFT features or histogram of gradient hog feature. And it was experimentally shown that performs okay for object recognition. And then convolutional neural networks, or CNNs for short, is a technique that has been known for a few decades. And actually, it was shown to perform really well in tasks like handwritten digit recognition in the 90s. But the approach there is that you rely on the model to learn also the features that matter for the application at hand. So the concept, they replace hand-engineered features. And the basic technique is that you have this layered system of neural network. The earlier layers, they learn lower level features, for example, the intensity gradients or edges of the scene. And as you go deeper in the network successively, these lower level features are composed to detect higher level features like corners on objects, local features of an object, and they get composed to actually detect objects very deep in the network. The good news is it performs a lot better than what we have in what we used to have. So it performs very well. And actually, there's a recent result that shows that if network is complex enough, you can beat human performance in object recognition, which is very impressive. The bad news is they're computationally very intensive. So if you want to implement them on an embedded system with limited processing or energy resources, you have a problem. To talk about how we go about optimizing this implementation, let me give you a sense for what this computation is. We are all comfortable with the notion of convolution. You have a sliding window with known weights, and this window is slided over a source image to generate a weighted average of the source image, which we call the destination or result image. In CNNs, the weight or the parameters are learned. In case of CNN, the convolutions are actually three-dimensional. So you have not one but a number of source images and not one but a number of output images. These are called feature maps for input feature map and output feature maps, just because it can happen anywhere in your chain of layers. And in this example I'm showing, the color coding goes with the kernel. So for example, the blue output feature map is computed by using a kernel stack rather than just one kernel, applied to a number of source images. The green kernel stack computes the green output feature map and so forth. So you can get the sense that this is a very intensive application, especially if you have many layers of it. Here's an example that won the 2012 ImageNet competition, the work done out of the University of Toronto by Alex Krzyzewski and his co-authors. Very well-known network, reinvigorated interest in CNNs in the vision community. And this example network has about 7 layers for detecting features, extracting features, and a last layer for classification. So the first few layers they have, the first 5 layers, they have mostly local connections, so they use locality to extract features. The last 2 layers, they are fully connected, so they can potentially extract global features as well as local features. And the last layer is the classifier. In case of AlexNet, which is the term typically used to refer to this network, is a softmax classifier to classify the given input image to 1,000 classes. That was the goal for the competition. We actually did some preliminary work on this, and there's, since this work was done back in 2012, and since then there has been other networks that actually perform better in terms of the type 5 error measure for the ImageNet. And in the examples we plotted here, you notice that there is a correlation and a rather monotonic relationship between how complex you make these networks and how well they perform in classification task. So it's, again, good news because we can do these applications more accurately. The bad news is it takes more resources to actually deploy them and compute them in mobile settings. So the challenge we're trying to address is how do you implement such complex computations on energy-constrained mobile systems? In terms of implementation choices, there are several options. One is the mobile system can offload the data, the images in this case, to cloud, and then potentially would have less constrained resources to do the computation. The challenge is network communication consumes a lot of energy, and for applications such as agricultural robotics or some drones in certain settings, the connection to the network is either unreliable or unavailable. So that doesn't make for a reliable solution. In terms of platforms that you could use to locally implement computations, you have the known trade-off between different choices of platforms. GPUs are currently the platform of choice. The challenge, though, is they consume about hundreds of watts of power, and in terms of energy efficiency, they don't quite compete with either ASIC or FPGA. ASICs are very costly to do. The volume and the maturity of the field quite justified yet, although there has been some effort to manufacture ASICs for the application. Specifically, we focus on FPGAs because of its attractive energy efficiency and cost trade-off. But the challenge is these platforms remain hard to use for machine learning experts and who specialize in training and configuring these networks. And the gap we try to fill is that can we have a synthesis scheme within a framework, for example, the Berkeley Cafe project, where a machine learning expert would experiment with the network, train it using a GPU, and once he or she is happy with the network, would click a button and an efficient implementation on the FPGA would be generated. So let me show you some vision we have with this project and some early results. In terms of preliminary work, we have some reference implementations for only the forward pass for the serving of the prediction with the network. And on the top right, what you see is the breakdown in terms of AlexNet of the number of cycles broken down between convolutional operation versus non-convolutional operation. In a CNN, typically you have nonlinearities, downsampling, and other non-convolutional operation. The blue shows what you have in convolutional, and it's clear that that dominates the computation. So for acceleration, you're better served to focusing on what convolutional layers do rather than nonlinearities and subsampling. And the synthesis process we do has a number of steps. It has to find the right representation for the numbers, mostly because floating point numbers are both quite unnecessary for hardware implementation and costly in terms of energy and area. And then approximation of these nonlinear operation, because some of them, like sigmoid function, to do them accurately in hardware would be, again, expensive in terms of area. So approximations are well justified, and there's work that shows you don't lose much accuracy by approximating your nonlinearities. In case of some nonlinearities like rectified linear units, you even don't need to do it because it's hardware friendly for implementation. And eventually we'll do a design space exploration to generate the architecture. And our underlying theme here is we would like to strike a balance between the computational need of the platform as well as the communication requirement. The challenge with CNN is that it goes through phases, and in phases the computation is compute bound, in certain phases it's memory bound. So that balancing act is important. For acceleration, there's a bunch of sources of parallelism that come at various granularities. Specifically, computation of different layers could be parallelized in a pipeline. Within one layer, you would have different output feature maps that you could process in parallel. For one output feature map, you have, within one layer, you have different outputs. For one output, you can parallelize for computation of different kernels in that kernel stack versus computation of the same kernel, because it's composed of multiple concurrent multiplication operations. And they come at different granularities. So if you are to strike a balance between compute and compute bound and memory bound of the application and make the best use of the resources you have in terms of logic density, on-chip storage, and communication bandwidth with the off-chip memory, you would need to find the right degree to exploit each of these sources of parallelism. And that's what we do in our design space exploration scheme. So specifically, we have this template architecture, which is an architecture that's parameterized to be able to exploit all these sources of parallelism. The details are in our upcoming paper that's posted on our webpage if you're interested. So given the short time I have, I'll skim through the slides and give you a feel for what our architecture does. We have this compute engine we call a parallel convolutional engine, or PCE, which can exploit the parallelism at the level of computing one kernel or intra-kernel parallelism. And then you have a number of these instantiated in parallel. So as they run in parallel, they can be used to compute one output. And then a number of these units potentially can be replicated, so you can compute multiple outputs at the same time. And our design space exploration figures out what's the right number of replications and the parameter for each of these blocks such that you would get the best performance. So in this case, you see the intra-kernel parallelism through the PCEs, the parallel convolution engines, and then the inter-kernel parallelism, and then eventually you can replicate this block to compute multiple outputs. And the essential idea here is that if you have the entire computation, you have parameters, you can parameterize this problem, and then you can do tiling, because on-chip memory resources are typically insufficient to store everything on the chip. You need to decide how much of each data you want to load to the chip, run your computation to the extent possible, and offload to the off-chip memory resources. So you can come up with these, parameters. Then for some reason, some of the lettering doesn't show up on my slides here, but the details are again in the paper. So you can have these parameters for how much of data you store on-chip resources, and that we call tiling. And this parameter is defined for all aspects of the computation, for how many rows of the input, how many columns of the input feature maps, how many input feature maps, what size of the kernel, and same parameters for the output feature maps. Once you parameterize it, then you can parametrically come up with analytical models for estimation of the requirement in terms of area, on-chip resource storage, and also memory bandwidth. Okay, and the idea is that your memory controller will load something up from the external memory. It will load the data either in input feature maps or the weight buffers, depending on whether it's the data or weight that you're loading. Potentially, you can double buffer to mask some of the latency of data communication. And then there's an execution pipeline and a buffer for output feature map. The output feature maps are either written back to the memory or they are reused in the execution pipeline because maybe your computation for one output feature map is not finished in one iteration. Once you do that, you can, in simulation, at least that's the result we have so far, come up with the roofline model, right? You can see in the space of computation to communication ratio on the x-axis, and the maximum ideal attainable performance on the y-axis, where these design points lie. So we have a lot of these points, and each point is derived by one point in the parameter space of the parameters I introduced earlier. And all these points are potentially design points, but you have a few design constraints to consider. One is that you have a memory bandwidth. So any computation that's on the left or top of this line, which have a higher slope essentially, requires a larger memory bandwidth that your platform supports. And any design point above of the area limit of the target FPGA, the logic density, is in effect infeasible because you don't have enough resources on the chip. And anything on the bottom and right would become a feasible, theoretically feasible solution. And among those, you can pick obviously something that gives you the higher attainable performance. And ideally, you want to pick something that puts the least pressure on the memory bandwidth. So we pick that point on the far right because the slope to the origin, which determines your effective memory bandwidth, is the smallest among the high computing solutions. So our simulation shows that this performs well. So specifically, we have 3 parts to this table, and this is the case of AlexNet for the 5 convolutional layers that I introduced earlier. The first part deals with the number of cycles if you assume that all the parameters on the network is dynamic, meaning that as you compute layers of the AlexNet or network CNN in general, you are free to change the parameters. The next part assumes that you change parameters that deal with the processing the number of input and output feature maps, but not with the kernels. So you always keep the PCEs constant in terms of the complexity. And the last part assumes that everything is fixed. So you see in the last part, the parameters of T sub m, T sub n, and T sub k are not changing. And this slide are ideal, so it assumes, it doesn't consider the overhead introduced by the capability to be reconfiguring between different layers. And even in the ideal case, you'll see that you can hope for at most about 20% in the ideal case improvement over the fixed parameter case. So the feeling we have, and you have some further results on this, that dynamic reconfiguration is not quite justified. You're better off figuring out what's the best set of parameters for the entire application, though that set of parameters will change probably going from one network to the other. So this is how our simulation results compare with other published efforts in this area. And specifically, there has been a number of works that either try to do an accelerator in ASIC, they synthesize a piece of hardware on silicon, or they do FPGA implementations. And our work, as you see the numbers here, beats them because of, I would say, the architecture exploration aspects, not because of the higher frequency or higher area, because the last row in the table, we normalize it based on the number of slices that the FPGA chip has available. Obviously, work done in 2009 would have access to a much smaller FPGA, a much older FPGA. So that last row is meant to normalize for the resources available to rather compare the architectural approach to the design problem. And to see how the approach would extrapolate to future devices if you had FPGAs that would give you twice as much logic and, let's say, twice as generous of a memory bandwidth. On the left side, you have the result with the Xilinx Vertex 7 485T chip. And we compare our simulation results with work done out of UCLA by work from Professor Jason Kong's group that was published in the FPGA conference last February. It's the best result we've come across so far, and we have some about 30–40% improvement in terms of latency for the same FPGA that was used in that work. If you used the same techniques, but apply the techniques to an approach that a platform that has twice as much memory and logic density, the gap would be widened just because of the larger design space points we consider compared to the previously published work. So with that, here's a set of references that are also available on the paper I mentioned and also on our webpage. And I would like to acknowledge the co-authors, two of my colleagues, Professor Akella and Boss, who have been involved with various stages of this work, and the funding sponsors. Thank you very much for your attention.